Steinhauer here, welcome back. We are continuing our discussion of properties of stars and how we measure them and quantify them. We've already seen distance. Now we want to talk about brightnesses of stars. And I apologize for this in advance. It's one of the most archaic and arcane and silly ways of measuring things in all of science. I'm not gonna lie. And it's kind of a pain and seems like it was made just to torture undergraduate students. I assure you that's not the case, but it is going to end up that way. Anyway, here we have a star field. This is the constellation Orion. We've seen this many times in this class already. The bright star Betelgeuse at the head and Rigel at the foot, and the three belt stars, some other stars, Bellatrix up here and Saiph down here. And Sirius, actually not in Orion, but in the constellation Canis Major, one of Orion's two hunting dogs. Sirius is the brightest star in the sky. And on this chart, you see, on this graphic, you see we've got the actual numbers that we use to quantify the brightnesses of each of these stars. Betelgeuse is 0.45, Bellatrix 1.62, Rigel plus 0.15, and Rigel and Sirius negative 1.44. So these are called magnitudes. We quantify the brightnesses of stars in this unit called magnitudes, which isn't really even a unit. So you'll notice some weird things about it. First of all, you'll notice that it's completely backwards, right? Here is Sirius. It's the brightest star in the sky, not just in this field, but in the sky of any star. And it's got a negative magnitude. It's the smallest magnitude. In fact, as you go fainter and fainter to Rigel, to Betelgeuse, to Bellatrix, to Saiph, to this really faint guy, 51 Orionis, the numbers, as the stars get fainter, the numbers get larger. So this is a backward scale. The smaller the number, the brighter the star. It's also a logarithmic scale. It doesn't even vary linearly. And that's in evidence, it can't be a linear scale since some of these things go negative. So why on earth would we do it this way? Well, there's something in astronomy, which is that once something does something a way, we're sort of stuck with it. And in this particular case, the thing that something did was well over 2,000 years ago. There was an astronomer named Hipparchus who, in the hundreds of BC, made the first catalog of all of the stars in the sky. It was a pretty amazing thing to do. If you imagine going out night after night and cataloging every star you can see, it's a massive undertaking. And he had obviously he was just using his eyes. Telescopes hadn't been invented yet. So he was estimating, in addition to their rough location in the sky, he was estimating the brightness of each of these stars in the sky. And instead he had no quantitative way to do this, so he binned them, right? He said, bin 1 is all of the brightest stars, and then bin 2 is the next brightest stars, and then bin 3 is the next brightest stars, and then bin 4 and 5 are the next brightest stars, and bin 5 is actually the faintest stars that he could see. Well, this is a very useful thing to have done. People used it for centuries. And finally, in the 1800s, when we finally were able to take photographs of the sky and take quantitative measurements of things, people had already been using this for thousands of years. And so instead of abandoning the system and using something more logical, we simply codified Hipparchus's scale and made it an actual numerical scale. So I apologize, but that's what we're stuck with now. We measure the brightnesses of stars in things called magnitudes. Okay, so why is it logarithmic, first of all? So it's backwards, you can see, because Hipparchus did it that way. He called the brightest stars rank 1, and then rank 2. So it was already set up to be backwards. And then the logarithmic aspect comes into how our own eyes work. Our eyes are logarithmic detectors, which is a very good thing. It gives us the huge advantage of being able to see very faint things and very bright things. But it's not a useful way. So in that sense, it makes sense that Hipparchus's original scale has a logarithmic form to it. Okay, how is this actually codified today? Let's take a look. This is the equation that you'll be using a lot over the next few weeks of class, the magnitude scale. And this is how it's defined. The magnitude of two objects, M1 and M2, the difference in those magnitudes is equal to negative 2.5 times the log of the ratio of their brightnesses. Okay, so a couple of things here. One, this logarithm is a log base 10, for those of you who are keeping track and need to know, and that's all of you. This is log base 10. We'll talk about what log base 10s are in a minute. But these brightnesses are the normal thing that you would think of as brightnesses, right? They have physical units. If you double the brightness of something, this B is what doubles, right? This has units of energy per unit time per square meter passing through your telescope or into your eye or something like that. This is a normal logical way to measure brightnesses. These are completely illogical ways, but if you do have these B's, you can turn them into a difference in magnitude at least. Okay, now you may be freaking out at this point if you have some math anxiety. Oh no, logs, how am I gonna do this? Let me set your mind at ease. Logs base 10 are fairly easy to work with. So let me prove to you that log base 10s are pretty easy to work with some examples. So it's probably easiest just to write down some of these things. So what is the log of 1? It turns out the log of 1 is 0, which may seem a little weird until you realize what the pattern is. What's the log of 10? The log of 10 is 1. The log of 100 is 2. What do you see as the pattern here? It's the number of zeros in the number. Now that's not quite all it is, but we'll get there in a second. So 10 to the 13 is a 1 with 13 zeros in it. The log base, this is all base 10, the log base 10 of 13, of 10 to the 13 is just 13. That's pretty simple. Okay, you can also have logs of numbers that are less than 1. So for instance, the log of 0.01 is -2. Why? Well, because you have to move this decimal point over twice to get it back to the 1. The log of 10 to the -5 is, you guessed it, -5. The final thing here, what is the log of 5,627? That's not a number that you can calculate on your own. That you need a calculator for. But what do you know? Well, you know that the log of 1,000 is 3, because that's just 10 to the 3. And you know the log of 10,000 is going to be 4, because it's got 4 zeros. So the log of 5,627 has to be somewhere between 3 and 4. If you plug it in your calculator, you'll find the log of 5,627 is, in fact, 3.75, which is between 3 and 4. So again, you're going to need your calculator for almost all of these, but you should, before you even plug it in your calculator, have an idea of what the number is going to be. Okay, now sometimes we're going to be given what the log is and need the log of a number is and need the number itself. So for instance, if we know that the log of x is 5, what do we do? To get rid of those logs, the way to do that is to take 10 and raise it to the power of both sides, right? 10, let's look at this over here. 10 raised to the power of log of x is x. That is the way you get rid of that log. 10 to the log x is x. And so if 10 to the log x is 10 to the 5, then x equals 10 to the 5. Or in this case, 100,000, which makes sense, right? The log of 10 to the 5, if we do this again, the log of 10 to the 5 is 5. So if log of x equals 5, it must be that x is 10 to the 5. If the log of x is -21, again, just take 10 and raise it to the power of both sides. X must be 10 to the -21. So again, if this is an integer, this makes sense and is easy. If it's not an integer, then you need to plug it in your calculator. But again, before you plug it in your calculator, you should know about what this number is going to be. If the log x is 2.451, well, I don't know what x is definitively, but if this were 2, x would be 100. If this were 3, x would be 1,000. So x has to be somewhere between 100 and 1,000. And if you actually plug it into your calculator, you get that x is in fact 282, which is between 100 and 1,000. This would be a question for you. You can try it off if you want. If log of x is 1, what would x be? Well, again, just take 10 and raise it to the power of both sides. 10 to the log x is x, and 10 to the 1 is 10. So if log of x is 1, then x must be 10. Okay, so hopefully that demystifies log-based 10. You're going to have to work in both directions. You can use your calculator, and the trickiest part of all of this is if you're solving for x and you're saying log x is equal to some number, but it's not that hard. All you have to do is take 10 and raise it to the power of both sides, and that gives you your x out and removes the logarithm for that particular situation. Okay, let's try this out for size. If star 1 is 100 times brighter than star 2, what are their relative magnitudes? Well, what are we given? We're given that B1, we don't know what B1 and B2 are, but what do we know? We know that B1 divided by B2 is equal to 100. That's what it means for star 1 to be 100 times brighter than star 2. So we can plug that into our magnitude equation. M1 minus M2 equals negative 2.5 times the log of B1 over B2. And in this case, that's just 100. Great. Well, we can do our log magic now. What is the log base 10 of 100? Well, there's 2 zeros there. The log base 10 of 100 is just 2. This is negative 2.5 times 2, which is negative 5. And that's M1 minus M2. So if star 1 is 100 times brighter than star 2, then its magnitude will be 5 less than magnitude 2. Interestingly, this doesn't tell you what each of their magnitudes is. The magnitude scale is only defined as a difference between two magnitudes. So, but that's a good thing to keep in mind, right? A magnitude difference of 5 always corresponds to a brightness ratio of 100. But you might see the problem with the scale right now. We don't have a 0 point for our scale. In fact, we need a 0 point. The 0 point is not defined by the system itself. And so we have to make an arbitrary choice. And the arbitrary choice that we've made is to set the star Vega to be magnitude 0 at all wavelengths. And once you do that, you can always compare your stars to Vega's magnitude, the brightness of your star to the brightness of Vega, and that will set the magnitude for the star that you're interested in. Vega is a useful star because it's one of the brighter stars in the sky, and it is high in the sky in the evening and the nighttime in the northern hemispheres in the summertime, which is when much of this observations, at least in the early times, was taking place. So that's our 0 point. And here is the whole magnitude scale, right? This is a crazy way, as I mentioned before, to measure the brightnesses of things, but it kind of makes our life a little bit easier in the sense that the entire magnitude scale of the brightest things in the sky to the faintest things that we could possibly see in the sky only encompasses about 55 to 60 magnitudes worth of brightness, even though we're talking about many, many, many orders of magnitude in actual brightness. So here are some things along the way. The sun in the sky has an apparent magnitude of negative 26.7. That's an extremely bright thing, obviously. The next brightest thing in the sky is the full moon. It's got a magnitude of negative 12.6. We already mentioned Sirius, the brightest star in the sky, with a negative 1.44 magnitude. It's not the brightest next thing in the sky, though, because Venus, some of the planets can be brighter. They change in brightness as they orbit the sun, and we get closer and further away from them. But Venus, at its brightest, is the brightest of the planets, and it's got a magnitude of negative 4.4. The naked eye limit of what you can see is about +6, and that's even at a very dark site with very good eyesight. All the stars that you can see in the sky from anywhere without some binoculars or some aid lie between negative 1.44 Sirius and the naked eye limit of +6. Every single star you see in the sky has a magnitude less than 0.6. Even with binoculars, you can get down to about +10. Pluto, it doesn't really change in brightness because it isn't moving very fast. It's about +15.1. It's very faint, can't even see. It takes a moderate sized telescope even to be able to make Pluto out in the sky. When we go to telescopes in Arizona, we're measuring the small one, which are 36 inches in diameter or so, are measuring brightnesses down to about +20. If we use our larger telescope, we can get down to +24 or 25. And if you spend a lot of time on the world's best telescopes, Hubble Space Telescope and largest Earth-based telescopes, you're getting down into the +30 range in terms of brightness that you can actually detect. So this is it, the entire magnitude scale from the brightest things in the sky to the faintest things in the sky. And remember our rule of thumb, every 5 magnitudes is a brightness ratio of 100. So these 25th magnitude stars are 100 times brighter than the 30th magnitude stars. These 20th magnitude stars are 100 times brighter than the 25th magnitude stars. Every time you go up by a factor of by 5 in magnitude, you're getting brighter by a factor of another 100 in the brightnesses of those things. So it's an enormous, we can count it up, 2 orders of magnitude for every one of these. Let's just count them up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 23 magnitudes or so, 23 orders of magnitude between the brightest things in the sky and the faintest things in the sky. 23 orders of magnitude. That's a 1 with 23 zeros on it, how much brighter the sun is than the faintest things we can see. Obviously, that would be a lot of work to write all that out. The magnitude system makes it easier because it compresses all of that range down into numbers that are varying by only at most 50 to 60 magnitudes. Okay, we'll stop there with the magnitude scale and come back next time and talk about more stars. Yay.